So welcome everyone. I speak English because we have guests here speaking English. So this is a Hong Kong government funded training from the industry department. Industry department. So today is a training focusing on architect or construction industry. So why we chose outer software as a training on the construction industry, because they have a very strong function on simulating the structural part. Back to many years ago, they already start this simulation program. However, 20 years ago, if the part being simulated to be very organic, it is very difficult to build a part. But now we have 3D printing. We can 3D print any shape, no matter how difficult to make it. We can have the part by 3D print machine. For example, like this. It is a bicycle.
No.
This part, if we have to make it in metal, assuming that it's metal, it is very difficult to do it by machine. But if we do it by 3D printing, we can do it, and even we can build only one pieces, we can make it. So they are very strong in this simulation software. That's why we invite Army come to join to conduct this training. And they see we have a very overwhelming registration. They send one more expert here, Tony, to help. If everyone have any question, you can raise to them. So I stop here and hope everyone enjoy the training today. So it's your time.
Welcome to the training. As well, I'm happy to be here, to have the chance being here. Yeah, my name is Armin. I started 16, 17 years ago at Altair. Worked in Germany most time. I'm now in charge of the technical team in China, working or living as well in Shanghai. And my background is, over the last years, doing service for a lot of industries, for optimization, topology optimization, shape optimization, whatever optimization. So that's a little bit of my background. Tony is with me. He comes from New Zealand, is an expert in Inspire, and has as well a very deep understanding of 3D printing. So we share a little bit the presentation. I give a more general overview of some slides about the company. And yeah, what he just mentioned is that we now can print, but actually as well, the 3D printing needs simulation and optimization to understand what you should print. And Tony, he will give much more information about the Inspire, the process, and examples and so on. I think it's a good match, both together. Later on, we have a kind of a hands-on training in Inspire. So whenever you have questions, you may ask. I think there's enough time to have kind of a workshop feeling, climate. You ask, we answer. So whenever you think I want to know something, just raise your hand and ask us. Okay, I hope you can understand myself well. So let's start. First, some slides about the company. I don't know whether you know Altair Engineering. Yep, it's working. So it's a company that was founded 30 years ago in Detroit. Detroit is an automotive city. So we come from automotive, working for doing service, and then developed software to be more efficient doing the service, and now the software business is our main business. We do We provide, develop, and sell our software, and do service as well in order to help our customers to solve problems. On the other hand, as well, to understand what is necessary in the future to improve our solutions. So we are worldwide, around 50 offices. Turnover is more than 300 million US dollars. Our software system enables you to use third-party solutions as well, because Altair does not cover all the possibilities, what you can simulate and what you want to simulate. So we invite a lot of software vendors to join our licensing system with some niche products, niche solutions. So when you work with Altair software, you can use a lot more than just what we provide by ourselves. More than 2,500 people all over the world. In China, we are around 110, 120 people. And yeah, 5,000 customers, and that's the more important number. More than 60,000 people use our software all every day, and that yeah, makes us proud to work with them. In general, I don't know the background of you all, but we concentrate on mechanical simulation mainly. Our main focus, like structural analysis, stresses, stiffness, for crash, so high deformation, fast deformation, thermal analysis. You have fluid mechanic inside, fluid dynamic, wind turbines, system simulation. That is important right now for all these controlled vehicle functions, like an comfortable suspension system or these autonomous driving. We do is manufacturing simulation, because somehow you want to produce it, and does that work? And that helps us a lot in the optimization process to understand in which direction we have to optimize our tools. And recently we added functionalities for electromagnetics, car-to-car communication, as well the mobile network, signal distribution, antenna design. So all over traditional mechanical software, and some products which are investment in the future in the new things which are coming up, like as well big data analysis, Internet of Things, and beside that as well manufacturing materials, manufacturing methods, and material science. 3D printing is an additional method that you can use, but you have to be you have to know how to use it, unless you're not successful. Otherwise you're not successful, and therefore we have our work. In addition, material science is as well a very interesting topic, because you start to customize the material as you want to have it. You can mix a lot of components together as you want to have it, and later on you get a customized characteristic in material properties. And that is very interesting for us, because we need these properties in our simulation. So in the past you tested a lot the materials, and then you get the parameters. In the future you directly simulate the micro mechanics of the material, and then you get the properties that you need for the simulation. So that's a brief introduction about Altair. Now we come to the workshop itself. So we have 3 people here. It's me, Armin, I'm from Germany. Then Tony, Tim, he's from New Zealand. And we have Jingbin you're from Shanghai. I don't know exactly from what city you are, but you work in Shanghai right now.
The city is Shanghai.
This is Shanghai?
Yeah.
Okay. So we work as a team inside of Altair, the worldwide team, and we are happy to be here and present this topic. So when you see, when I would show that slide to my kids, they would say, hey, cool printed stuff, you know, but actually that is not printed, so manufactured a long time ago, and that does not mean that if 3D printing gives you all these possibilities, it's new. Actually, you was able to do it, but a lot more effort. And that was taking away material step by step out of wood, really well made. And the modern method is to add material step by step. The outline of my presentation, I give a little bit an introduction of 3D printing. I think you know more than I do about 3D printing, but I want to sum it up to that point that is important for us as a simulation perspective. What is necessary to print successfully? Optimization is very important. How did that develop over the time? And how do you get optimization results into a design, CAD design, so that you can print? So what is it from my perspective, from a simulation guy perspective? There are a lot of methods you can use. I saw that down there in the lobby. There's standing a lot of printing machines, different methods, but all of them have one thing actually in common. You place material, liquid, or whatever material it is next to each other, and you try to combine them. Different ways, with a laser, with a ultraviolet light. Here you melt it, and here you have laminates, and you bring them together. So different methods, but one in common, you add step by step the material to the other ones, and that gives you the freedom in the design. But there's one, drawback. You have gravity, unfortunately. So when you have a shape without a support underneath, you have to add some support structure. That is necessary maybe later on when you bring the design into the printing process. Most printers, as far as I know, use just one direction you print. It's mainly in Z direction. So against the gravity vector. And therefore you need the support structure that you have to consider, and you have to consider as well to take that out later on. Maybe you can place the part in different way in your printer, so you print it in different directions that can save material or can add more material for support structure. That depends. So what is the characteristics of 3D printing? We heard already. You can have a lot of freedom to produce different shapes. You have actually no upfront investment beside of the material and the printer itself. So you don't have to do some tooling before you start with the production. You can just push a button and get it printed. It's a direct manufacturing of the part you want to have. Or the other way around, what's used a lot is actually you print the tool. Later on you use other manufacturing methods like casting to produce the final product. And these kernels or tools, they can be made out of different kind of material, as well as sand with polymers inside to get it so that it sticks together. The lot size, so number of parts can be just one. That's very good for spare parts when you just need a very low number of parts and you do not have to keep them in storage over long time, and you just print it when you need them. You can customize them. That is for one example that we have for bicycles. There's a general design for the bicycle, and then for every customer they just adjust the design a little bit and print them and get a customized bicycle. The negative part is it's slow, it's expensive, and somehow for some cases or use cases you have to treat the material later on, especially when it's for high strength and high pressure usage. You have to treat the material later on with temperature, for example, so that is say a disadvantage. And it is much more than just buy a printer and you start printing. Otherwise you burn money, and actually you want to print money with it. So it's and that's where we come into the game. We help to identify the right shape so that the customer expectations are met, and we help to optimize the design, reduce the weight, so that you have an advantage later on. So yeah, that's about how to print successful. Customer expectations are varying. A lot of different expectations. Yeah, higher performance, cool design, should be lighter. So besides cool design, that is easy. You just have to look, concentrate on the shape and how it looks like. But to have it lighter and a higher performance, therefore you have to do much more. So 3D printing is a method to help to produce cool things that you could not do before. So it transforms these design ideas into reality. But how to get these ideas? That is the point where simulation comes into game. That's a small. Oops. Yeah, it works. So, small video what simulation is. So you look into the parts itself. You look how they perform. You find out the stresses, the load cycles they can stand for durability, for example, and that's where simulation is used. And you define, but therefore you have to define the target first, and that is very important when you do simulation and you do optimization, that you define exactly what do you want to achieve. So what mechanical behavior characteristic you want to achieve, because when you do optimization, you target your design directly down to that specific performance characteristics, and that has to cover later on what you want to have in reality. So it's quite often the case that we optimize something and later on the customer comes, hey, you forgot to add this and that function, and therefore it's good to have a good understanding from the beginning in which direction you actually want to go, what should be the task of the part later on, and then you can give that job to a machine and create the shape. You get these design proposals. Later on, you test them and improve the design. You check if they are stiff enough, if they have the right stiffness, have the right stresses, in comparison with these material parameters, so these stresses they can stand. And the shape, and you simulate even the printing process. So altogether, you have a closed loop thing here. For us, it is important to understand these expectations, to define the targets of the product we want to produce. We generate the shapes, how it looks like, and later on with the 3D printing, you can print it, and then the high costs are say justified because the expectations are met from customers. It's more or less everything about the shape, manufacturing method, material, to meet this balance circle between cost, weight, and performance, so that you have the final advantage in the market compared against different other competitors or other manufacturing methods. More about the simulation and optimization. So that's where we live on and where we grew up. In long time ago, 30 years ago, you had 2D CAD and manual design to define the shape. Later on, 3D CAD came into the game, so you had more freedom to design stuff on a computer. And since 2000, roughly, the simulation-driven design approaches were more and more used and introduced. So that means simulation-driven design is, you can explain like the computer is taking decisions. It's not only that you give him a job to solve the stresses or the performance. No, you define the target performance, and itself runs more variants, and finally it comes up with an idea what the perfect, optimal shape will be. On the product validation side, that's more like you have a shape, you have a material, and you check the performance. And as well in this area, prototypes and physical testing is getting, say, lower or less used, and CAE is picking up more and more, and you see that in some certification tests for vehicles, as well for aircrafts, can be done just based on CAE, and you do not have to do any testing anymore. For sure, you have to invest in material knowledge, in manufacturing knowledge about manufacturing process, and as well in knowledge how to model it, how to represent the reality in your mechanical or mathematical model in the computer. Then you can be sure that you really meet the effects, physical effects in reality, and you can do full testing and certification in the computer. So simulation-driven design, as I said, is the computer takes decisions, is optimizing. It's nothing that you can do just by some math functions. So Tony actually put that together one time. I don't know where you found these formulas. So it's a lot of math in the background, and some guys at Altair, actually they wrote their own optimization code, maybe in university, so they understand that, but every customer would look like that when he sees that and has to deal with it. So that's our job, and that's where we live on. We make that easy to simulate, make it easy to use. Very, very simple showcase. That's where the bridge, how big the bridge can be, and that's what you would assume as an engineer should be the support structure finally. And you give the same task computer, and you get a result out of it as you have expected it. That is easy with a simple design. You can do that by your own still. With a lot of experience, it's not a problem to do that. But when it is a very complicated situation with a lot of different load cases that come up and a lot of stuff you have to consider, then the engineers, yeah, they struggle with it to capture that and to work that by hand and based on experience. So this is why the optimization is necessary to capture that and to combine a lot of different effects into a simulation and generate the optimal design out of it. Some practical example, or one as well, or an illustration here. You have a load on a part, you generate the shape, and later on you try or you bring that into reality. That's an example here for an automotive part. It was end of the 90s, what we simulated. That part was a bracket that was not holding the loads. So we brought it into the simulation optimization method, and step by step the computer simulated or calculated where the material should be placed. And finally, the final design was lighter. You see a comparison between both, and could hold the loads. So that is a very simple practical example how that works. Here another step-by-step graph. You define the possible workspace, how big the part can be. Then you define the forces which will act on the part. You define the target, stress, stiffness, weight, whatever you want to define. You can define a lot. And then the computer step by step calculates where the material should be. You do that not only for a simple part, you can do that as well for a full vehicle. It's a study that we did some years ago with Opel. At that time it was General Motors, now it is Peugeot who owns that knowledge. So we defined a full, rear end of the vehicle as a design space, and told the computer, that's your job, do whatever you want to do. Of course, we defined the attachment points of the suspension, the crash loads. We had to define where the passengers are sitting, and then we got a design out of it. Okay, it's not that you can produce it with traditional methods right now, so we had to work with the designer, with the technical designer, how can we bring these ideas into reality. So that is a step, what is absolutely necessary for a vehicle design where you're not that flexible with the manufacturing models. 3D printing helps more, but I have not yet, there are studies of 3D printed cars, but none of the mass production OEMs is using that yet. So we will see that in the future, I'm sure, but right now you have to work a lot how to interpret it and bring it into the final design. This is just a slide to give you an idea with what companies work with. Ferrari, since 5 years, is setting up the new platforms based on these optimization methods. Daimler as well, the new EV platform will be based on this technology. China-based companies as well. They are working in Sweden, but they are owned by China companies. BMW and Peugeot and Renault are our customers as well. So actually it's the same technology we use here for these projects as you have in Inspire, what we will have kind of a short introduction training later on. So how did that optimization was developed over the time? And so end of the 90s, when we started to use it, it was the aerospace which was pushing that method a lot. There were 3 programs going on in the world. That was the A380 in Europe, then the Airbus D50 as well in Europe, and the 787 Boeing in Seattle, which were 3 programs which introduced this method into the development process. So at that time we started with a blank, a plain model. At the beginning we used the loads, we get the result out of it, and then by hand we extracted the geometry, and later on it is actually produced like this, like that shape, and saves 400 kilos for an airplane. So a lot of return on investment, and now this optimization method is fully integrated in the aerospace design process. And but we saw that a lot of other industries would like to use this optimization, but then they said, hey, I cannot produce that, what we generate with our optimization. So our engineers were sitting down and introducing manufacturing constraints. So they guide the optimization towards a certain direction. So max member size, for example, for molding processes, where you try to avoid regions with a lot of material because it shrinks and then you get problems with it. Draw directions as well, another manufacturing constraint, because when you have a torsional loading, then hollow structure is always the best, but it restricts the manufacturing later on. So that design for certain manufacturing equipment that you have already, you can build that and still have the optimal design later on. Then it's extrusion, especially for aluminum profiles, for facades, or as well in automotive, used heavily without and with extrusion constraints. It helps you to tailor the design already towards manufacturing method. And then no holes, for example. You see the difference with and without these manufacturing constraint, and one for forging as well. The difference that is here, it's a hole inside which you avoid in the other design. But step by step, the more manufacturing constraints you apply, the less performance you finally get. Without any constraints, you have really good performance weight ratio, but symmetry, draw direction, member size, cyclic repetition, and so on, always constrains the design and reduce the performance. That is okay when you methods for production are restricted, and I think you know that these 3D printing is now an option to really unleash the potential of an unconstrained design. So we use that in the daily work always to have at least one simulation without any constraints, so we know what the maximum target is, the possibilities in performance and weight ratio. And then we see what method reduces the performance, but now you can really build what you want to build finally with the 3D print. So it's an example from AP Works. It's a company I think owned by Airbus. They concentrate on 3D printing in general, how to introduce that into their production. And they had a bracket, traditional design, and with optimization and some constraints, of course, they got that design, and finally you can print it, and it's like. So, and then another example, it's by General Electric, aircraft engine. The fuel nozzle, you see a lot in the press, in the internet. It is a 3D printed part in their aircraft engine, and it's a very complicated structure and geometry. The advantage why they do that is not only that it is lighter, but it combines a lot of parts together. So you do not have to assemble these nozzles out of a lot of different pieces. You just print it in one piece. And that's the second point. With this opportunity of free design, you have to think of how can you use that advantage, or how can you use this as an advantage to combine functions in one part, to change the borderline between different parts in an assembly, where to place the functionalities, borders of functionalities. So that's a lot of stuff you can, a lot of freedom, and when you use this freedom, then you get more commercial benefit finally, and you get as well a reduction in the production, reduction in the production cost, and as well in weight saving. So when you do this optimization, you get nice, cool pictures from OptiStruct or from Inspire. But what do you do later on? How can you work with other people, from design people, and discuss it and bring that into an assembly, for example? You need somehow a geometrical representation, a CAD design. The traditional CAD, conventional CAD, is based on Boolean rules and steps, and it is more or less the same as you produce parts. And when you want to bring that into a design, a CAD design, then you're frustrated because it's not going to work. And the best way is you don't use any CAD. You directly go from these shapes that the optimization methods generate into a direct geometric representation, an STL model, for example, and you skip all these CAD stuff. And the valve block, an example here from the optimization using a smooth functionality, and later on you directly get an STL model, and you can print it as it was optimized in OptiStruct. So we worked on this direct modeling. It's a part of solidThinking now, where you are able to capture the design or the results from optimization, as you see underneath here, with surfaces, with surface representation quite easily. You will see more later on. And you bring them together, you join them in a very easy to use way, quite fast to do it, and gives you a lot of freedom to change, to adjust the design and to modify it. So now you join them as well, bring them together. You see it is a click solution. And the next step is when you generate this geometry out of an optimization proposal from a optimization tool, you want to check it whether it's really working like you want to have it. Yeah. And therefore you directly apply the loads, the load cases. You should have used before for the optimization in the first step, and you get the stresses and the deformation directly in the same tool. And when you're satisfied, then you can go into the print process. If you want to modify it, then you can modify by hand, adjust it, or you can redo the optimization or adjust some optimization parameters, because there are a lot of options to guide and to tune the optimization process. Some further examples where that step-by-step method was used. Piston for automotive, mainly weight saving as a target. This is bicycle components, the joints of a bicycle as well. Weight saving 40%, but I would say is as well the possibility of to customize the design is as well an advantage. In addition to weight saving, then this bracket we saw already. Then with RUAC, it's a part which is going to space. It's a part on a satellite, so it's really not a mass production. Only 2 or 3 maybe were produced. Very interesting work I can show later on, and that is as well a bracket where you save around a quarter of the weight. These bicycle example here, to customize it together with Renishaw, used it for Robot Bike Corporation, which was the company we worked with. Okay, the tone is not that important right now, but mainly it is that there are a lot of load cases and that you have to consider when you do this joint design. And in order to have that withstanding all the all the loads, and to make it customizable, you use that as a titanium printing process, and you can go on a website and put in your size of your body. Everyone is different, so they calculate the angles of the tubes in a bicycle and derive the shape of the joints, and then they print it, and you can get customized bicycle just built for you. Of course, withstanding all the loads that you generate. Same workflow, design space definition. What space do you have? It's well related to the printer later on, how big that is. You optimize it, you interpret it, you derive the geometry out of it, and then you check whether it really withstands all the loads, and you have to compare against the material properties. Yep. That's the final design, the initial design, final design, much lighter and one piece, and here it was a combination and an assembled part. Next example, it's from the company Amazon, Amazone, not Amazon, Amazone. It's a completely different business. It is farming machineries. As well, they are very innovative, and that part is a welded part with around 17 meters of weld line, and a lot of pieces have to be put together. To avoid that effort in manufacturing, they were thinking of casting. So that's the first step, and using optimization. And the next step was to use 3D printing, not to print the part, but to print the tool for the part. That's Inspire. So Inspire was used exclusively for that project. You do an MBD simulation, a motion simulation. You get the loads which apply or which are applied to the part. Then you define same steps, design space. You run the optimization. You get the design. You interpret it with the polymorphs, and you recheck if it will work. And then you go into printing, and that is the tool printing process of the later on casted parts. It is actually sand, which was what was used for these printed kernels. So at the beginning, initial part already optimized with casting, boundary conditions, manufacturing constraints, already lighter, cost reduction because of less welding lines, but then 3D printing form, even more weight saving, and time reduction for the tooling process because you print the tool and not machine the tool. These bracket for the satellite. Aluminium was the initial idea to use aluminium, and then we introduced the optimization because they thought, hey, we can print it as well. It's built out of titanium. So that was the interpretation of the design finally, and then it was tested in terms of the strengths and stiffnesses. So as that part is not allowed to fail at all during the launch, it's only around 5 minutes that has to see loads, or that it will see loads in space. There is not a lot of vibration. So in order to be sure that it will withstand the loads, they actually printed 2 parts at one printing process. The one part was tested, and when the test was good, then they used the other part to mount it to the satellite. Otherwise, they would not have been sure that the material property is fine, that all the parameters of printing process were defined in the right way, and so on. So quite some effort, but the part size, what you call the number of parts they had to print is maybe 5. Another example, step by step, is a camera bracket design on an airplane. You see the camera here, the bracket. So that's the initial design. Then you Does the video start? Yeah. Same step, design space. You work on the optimization and you get a cool structure out of it. I hope you have, that's the main point, have considered all load cases so that it will stand it later on. Then you use the pooling nerves to derive the geometry out of it, and yeah, and you test it, and you print it, and you have a much lighter and stiffer result. So the mass was reduced by 40%, and actually the deflection was reduced as well, so it was stiffer finally at the initial design. And then we think always, hey, what will be the next step? 3D printing is good, but what can you do later on? And these are the lattice structures. You do not have a solid material for a section, you have actually a lattice structure for a section. And you combine them, you have solid parts and lattice parts. Tony has a lot more knowledge and as well examples about this. And then you see that you further improve the weight saving compared to the just printed solid part. So that is the next step to use the freedom of 3D printing, not only for this aerospace part as well in architecture area. It is used, or people use the possibility and find out how can they use it successfully, so that I have really an advantage later on. So that's give you an idea how 3D printing and optimization work together. I heard it quite often that 3D printing helps the optimization guys like us to bring our ideas into reality. I would say it's as well the other way around. We help the 3D printing guys to really achieve an advantage beside the nice shape. What can be done? So we help to get the mechanical properties, the mechanical characteristics optimized, so that you have a real advantage based on weight saving and performance increase. And yeah, I think it will take a little bit time unless I see these buildings printed. At least they are optimized in Inspire. Can look like this in the future, and for architectural usage, Tony will give more details about it. All right, that is a picture of a 3D printed bike end. That's the damper of the rear wheel lever, right? What do you call it? Suspension. Suspension, yeah, from the rear wheel. And that was just a picture, I can show more later, done by Airbus. They printed a bike, electric bike, used our technology, optimization technology, to get the design out of it. And it's a really cool story on the one hand, but as well proof that the method can be used beneficial and get very, very light design out of it. Okay, thanks a lot. So that's what I have to show. You have questions, ask me, so that I get at least as well a little bit feedback in which direction your interest is and what you want to know more about. I'm open for that.
I think there's coffee.
Well, that's what you want to have, yeah? So you want to have, you do not want to have questions, you want to have coffee. Okay, all right. If that's where you're looking for, we can do that. No problem.
So questions may be related.
I mean, coffee will help.
if you've got questions now.
Yeah. All right. I don't want to stand between you and the coffee, so go ahead. And of course, you can just ask me and tell me when you want to see something.
出邊準備咗啲咖啡啊、奶茶、水嗰啲俾大家。
As Armin introduced me, I'm from New Zealand. The downside is that we speak really fast. I'll try and slow myself right down to me and not be too quick. So the first slide, just to give some of, actually the second slide. This roughly what I'll cover is more of a like a design optimization overview. So Armin's covered some of the stuff I'll be doing, but I think it never hurts to repeat it anyway. Because if we just pummel it into you, by the end of the day, you might remember some of it. Then I'll talk about the basics of Inspire, some of the highlights that it's maybe not so important to you because you're not really familiar with Inspire. The stuff in there that people don't know about, some future things that are coming. We've got lots of nice, pretty pictures and cool examples. I'll demonstrate the whole process. I've done it in videos, and then if we've got time, I can just run through a little workshop problem, something very simple that you can maybe try and do yourselves, or we leave that to the end of the day if we've got spare time. So, just a little bit about me. I'm a mechanical engineer. I've got a master's from Auckland in New Zealand. I went and worked in the automotive industry, like Armin. Spent 6 years at Ford in the UK doing powertrain design. And then I joined Altair 20 years ago. Next month I joined Altair. I've also run my own consultancy. I've done the business in Australia. But throughout the last 20 plus years I've just been really passionate about the use of topology optimization in design, not just to get, I mean Armin's probably more of a German engineer than me, so he's maybe, you know, he wants the result. I'm really about using it as a creative tool a lot of the time, just to generate ideas, maybe throw the ideas away or just use a small part. But just use it for design engineers, for weight and cost reduction, improved performance, but lots of creativity as well. So hopefully we'll see some of that in some of the slides. And I kind of throw these intermediate slides up with stuff that I've tried to keep it things that I've had some involvement with as well. So then if you ask me hard questions, I know I might know the answers. So, you know, one of the things is it's not just really small stuff. We can do lattices at sort of a micro scale. We can do huge stuff like bridges, buildings, in this case a digger arm. So, you know, and that combines the multi-body dynamics with actuators, with the topology optimization. So there's no real limit to what you can apply it to. So that's the only limit is what's in here. So we talk a lot about optimization, and I think one of the best things is to prove something is to demonstrate the opposite. And what design optimization is. So there's an example of the four bridges over the TAF at Pontypridd in Wales. So the first bridge, they built it and it fell down. The second bridge, they were building it, wasn't even complete, it fell down. So make a design change. Third bridge was complete, and the heavy haunches pushed the middle up and it collapsed. Fourth bridge, made some design changes, it's still going. So they designed it, they built it, they tested it, it's slow and expensive. So that's not design optimization. But quite often you talk to people, they say, oh, I've done optimization. No, they've made changes, tested it, that's not optimization. What is optimization? So I used to have all Armin's equations just after this slide. And they came from a guy, Professor Vasily Toropov, who's an optimization guru. So I went on a course of his about 20 years ago, and that's where those equations came from. So what is optimization? The physical problem is you want to get maximize. You want to get to the best place possible. So it comes from Latin, the best, and you want to go up the hill. So you want to minimise or maximise. You want to maximise your height. You've got fences. You can't go outside those fences. So they're the bounds on your problem. They could be manufacturing constraints. And how do you get to the top? You change inputs. So it's going to be the angle that you go up the hill. But you have to decide what's the best angle. You have to decide what you do when you hit one of those constraints to turn around, to try and go straight up the hill. So all those equations really just help. They define that path up the hill. And you want to do it as quickly as possible because you want answers as quickly as possible. So again, it's not just getting a better result, it's getting the best possible result. That to me is what optimization is. So again, I've been doing similar things to this, similar talks for a long time, and I came up with this idea in February. I had to have a talk in the UK, and it came to me that all design is about responses. Now I'm not a designer, but it's just what are those responses, and a lot of the time it's the aesthetic response, especially in architecture. It's how people respond. So that's a really hard one to turn into an equation though. It's this other stuff like time and weight and power consumption, fatigue life, they're all responses as well. So you've got these design variables, things you can change, where you put material is often into your model. These different responses come out, and optimization is getting the best or achieving the best responses by changing those inputs. So it's always going to be compromised. It might not look as good if it's cheaper. It might not perform as well if it looks good. But that really is its design. So if anyone disagrees with that, I'd like to know, because I quite like that stuff. So simply, once you've done the optimization, it gives the best possible designs faster. So what is the best? It's different for different situations, different industries. It's better stuff, it's stiffer, more durable, cooler looking, low cost. And generally you get it faster. You don't have to build 4 bridges. You just build 1 bridge and it works first time. Just lower development costs, get to market quicker, right first time. So again, that's the other side. Not just better stuff, but a better process as well. So those examples are Altair first released OptiStruct in 1995 or 96. So it's been around a long time, and they're various examples that have the real ones, custom examples over the years. So lots of industries, lots of different applications. So historically, manufacturing limitations have constrained what the best is, and we've been doing this for 20 years, or not just us, commercial tools for 20 years, and you get these really optimum designs, but you can't make them. And 3D printing's part of it, but even more recently with composite structures, you can break down all the laminates, you can 3D cut them out, and robots put them up, and so it's not 3D printing, but it's kind of automated assembly, which again allows these very complex structures to be made. So finally, that this really these cool optimized things, and we can actually build them, which is quite nice. So I like to put real numbers on things if I can. So this was something I was involved with before, and I've got the numbers. 1 engine mount bracket on one Ford Focus car. Took 100 grams out of it. The reason we looked at optimization is it was braking, was it performing, was it hitting frequency targets. So we took 100 grams out. While we were doing it, we thought, the nice idea that came out of it, we thought, oh, that design change, we can get rid of a bolt and use a stub, 35 cents per bracket saved, 1.3 million produced, 1 bracket, $650,000. So that's pretty amazing savings for one high volume thing. And the converse is true. Lower volume things, the maths works out a bit different. So this is the wing ribs that Alan mentioned on the A380. So there were 13 ribs total that they designed. 500 kg saving across the aircraft. if you work out the fuel cost per kilogram of material, so $15,000 US per kilogram. For the operator of the aircraft, that's a huge fuel saving. So you actually find that the first aircraft, the first maybe 15 aircraft that come out of the factory are almost given away. So with 380s, Singapore Airlines, I think, got the first 2 380s, making you pay for them because the fuel cost on them is so much higher than aircraft under 50 where all the weight reductions start coming in. So it's not just Airbus, the same as on the 787. So we use all these, you get all these cool answers, and you know, the best view is a different thing. You know, I was in a meeting about 10 years ago, and the director of engineering design said to me, he looked at the results, he goes, it's a thinking tool. It's a thinking tool. You don't even need to use those results, it just helps you think things differently. And I thought, wow, that was a great quote. And then he carries on and goes, oh, it gives you hindsight before you've even started. Two of the best quotes I've ever had in the same meeting. So, you know, Armin also touched on this. If you do optimization, you have to define the responses you want, and just that the requirement that you know that you need to hit a frequency target, or you know that you need to hit a mass target, so just, or what fatigue or whatever. So just asking those questions at the beginning is just a really powerful thing to do, and doing optimization forces you to do that. So that's another cool picture in the background. So this is just the polynerves that Armin touched on. You can very quickly generate very complex shapes with the polynerves. But now, next bit of my talk, a little bit about Inspire. Just kind of going over it, getting you ready for practical workshop later. So, Armin showed lots of these little circle of life photos where you start with your design space and you work around to get your final result. So to me, there's just 2 or 3 underlying concepts. The first one is, given a design volume, so that's the maximum space you can play with, and you can see that in brown. You can put manufacturing constraints on that, symmetry, draw direction, or not, because you'll get a more optimum design. And then you've got non-design areas, so they're where you're going to have loads go on. If it's a bridge, it'll be where the cars go on the bridge, or where it attaches. You need to know your loads. You need to know where it's going to be supported. And then you need to really understand the responses that you need to control: displacement, frequency, mass. And what the topology optimization does, what Inspire does, is gives you the most efficient material layout. It says how to connect my load points to my support points in the most efficient way. So that, in one slide, that's what Inspire does. It takes a little bit more effort to make it work, but not much. And it fits into a typical design creation process, because so often I see parts with these rib structures that always run at nice constant angles. And I keep asking, why did the designer put ribs like that on, or the ones to the right hand side? And the answer is that as engineers, designers, architects, we've just gone through life seeing all these influences. It's, you've seen existing designs. You might not understand your load cases, so you play it safe. You build something that looks like whatever's already out there. The standard design methods, if you're doing hand calcs, it's much easier to calculate stresses from straight things than curved things. Lack of freeform CAD. If you can't put nice curves into your CAD, you're not going to design them like that in the first place. So it can be really hard to think of new ideas, and that results in suboptimal results. So topology optimization helps you break free of those paradigms. So no more paradigms. Just replace all those preconceptions with some design freedom. So again, you've got that grey exterior surface, so that can be a non-designable region, and then your yellow in the middle, that's your designable. So things like a plastic chair, you might have your custom surface at the front. You can't touch that. You can fill the back end with designable material. That doesn't have ribs on it. but the topology optimization can tell you where to put the ribs. So again, that customer surface, don't touch. Design freedom. What do you do in the background to make it structurally good? So the process, really simply, you've seen this a few times now. You get rid of the assumptions, remove those internal ribs, put some design freedom, and then you get a new design at the end, which again, without going into details, but you can single click at that result. You can get stress results. You know if it's going to perform. So again, those two quotes, thinking tool. You get a better starting point. You can look at different configurations to see which one gives you the best result really quickly. Better designs faster. Hindsight before you start. So it's very, very powerful. And then maybe 2 or 3 years ago, even thinking of printing a result directly was still way out there. I think we're actually getting really close to, we'll get a result. Okay, we can directly print a result now, but you want it to be smooth, you want it to be aesthetically pleasing. So fitting, cleaning, smoothing the result to get stuff that is basically really clear with the 3D printer. So we're getting closer to that, and especially with some of the lattice stuff, I think we will be there very soon. So we've talked, and pretty much all the examples have been topology, so that's where should the material go. There's another thing that's in Inspire called topography, so that's for sheet type structures to make them stiffer. So the back of your fridge, we see like swages and beads and things. This is a VW example from a while ago where they stiffened up the muffler on the car and got a 10 dB reduction in the noise. So even in architectural panels you could do that, or facades, or where they have frequency targets and the wind doesn't buffet them. So yeah, there's some really nice stuff you can do in topography. We've also got gauge optimization, so that's the thickness of the parts. So again, this is part of the car, it's called cross-car beam. 20 plus parts, 50% weight reduction. Took like an hour to do it. So really simple, fast cost savings. Again, if you've got any kind of sheet metal kind of fabrications, it can be very, very helpful. Well, I'm talking too fast. The multi-body dynamics coupling, which is as your mechanism moves through the range of motion, you can extract the loads and feed that into your model. It's very, very, very powerful. It's been covered, it'll be covered again, so I don't need to dwell on it too much. In the next release, which actually was beta yesterday, so it's almost there. A lot of the polygons functionality has been very enhanced. So in the past, it's easy to use, but you have to learn lots of tricks to get what you want out. We can do a lot more stuff now, things like just booleaning them together. So it's a much slicker process to get kind of complex connections sorted out. And there's a lot more features in there as well. Spot welds, and that would include rivets as well. You can very quickly join spot welded panels together. You can look at the stresses on the welds and the structures, the frequencies. Again, nice. With Inspire, everything's simple to use. That's our mission. And optimized lattice structures. You'll be seeing quite a few more pictures in the next few minutes. Part of my job is working on getting new features into Inspire. So I've been working the last couple of months on how we implement the lattice structures into Inspire. And again, it's quite a complex thing, but we've got it down to 3 little input boxes and a tick, 3 numbers and a tick box. So hopefully that will be enough to get some pretty exciting stuff coming up. So you can see there the beams are tapered. So our process with the lattice structures is to build a mesh and then optimize the radius or diameter at each end of the beam. So you get these tapered beams all through the structure, which gives some really, really nice looking results. So other people do lattice like mapping your lattice onto your parts for 3D printing, but that really is just map conformal, like a consistent lattice onto your part. We actually optimize it for structural performance. Lattices gives a few challenges. I might dispute something here. If you have a solid thing and then you take material away, it doesn't perform as well. So for the equivalent mass, a lattice structure will not perform as well as a solid structure. Sorry. But it has some advantages as well. So things like if you've got thin skins and you support them internally to prevent buckling, you can get much better performance. If you've got structures that need airflow through them, maybe cooling systems, better performance there. So they're fantastic, but they need to be used with caution. In things like aircraft industry, where they want to inspect parts, looking for cracks, they're really scared of lattice parts. They want something they can see everything. If you need to put, say, corrosion protection coating on them, they're very hard to do that for. So they're great, but they're not going to solve everyone's problems. The other thing I've been really struggling with, I've got a pretty high performance laptop. The file size of these lattice structures is huge. So you generate a lattice, you want to take it to your 3D printer. Standard method is for an STL file. Created one this morning that was 4 gigabytes, the STL file. Fans go on, the laptop starts lifting off the desk, it gets so hot. So even just handling them starts to become a bit of a challenge. That's doable, but just beware. But they are some of the structures are very custom. Things we're working on, so we've talked about if you have you need support structures. So we've actually now got optimization that takes into account the overhang angle. So we'll optimize, just like you might have a draw direction. It's so new I haven't got pictures in. So we'll do an optimum design that can be printed without any support structures. That's really cool. And we're also looking at the warping. So as your 3D printed parts cool down, they warp. So if you can predict that beforehand, you can print it in such a way that as it cools down, it will be the final shape that you want. And that just sort of minimises post-processing, realigning holes, heat treatment, things like that. So we're working on those for the future. So hopefully, I think you're cool examples. So I've got lots of cool examples to show now. And this is the famous Renshaw Altair facade bracket. So I did not the original optimization on this, but I did the lattice optimization on this. It uses it's a mixed method where within your design space you set some magic parameters and you'll get the most optimum distribution of solid bits and lattice bits within that structure. So you can see. Is the pointer on this one?
Yeah.
Yep. So you can see the kind of the solid areas up here and up here. But you get it's these transition zones that I actually don't like, and most people would prefer sort of a cleaner lattice to solid transition. So for the parameters we set, that was the optimum result, and you get these very nice looking lattice structures out. So you can see there's a slight taper on a lot of the beams there. So for the lattice that's there, it's been optimized. Now I've got more lattice coming up. So this is it's called a cross member just in card. It's just a bit of a design study. So this is it should be different. One of them's the one on the left is a no manufacturing constraints. So it's hollow, could be 3D printed in theory. The one on the right using a draw direction, so it could be cast. So the weight difference with between those is about 20% for the same performance. So again, if you can 3D print something, you'll get better performance than using traditional inputs. I'm a Mad King mountain biker, so this is another mountain bike bracket. I'm responsible for a few of them that are floating around the place. So again, going into the lattice technology, great idea, performs really well according to the analysis, but would you want that on your mountain bike? You'd get dirt all inside the lattice. It might start out as a really lightweight design, but by the time you got to the end of a muddy ride, it'd be full of mud, and probably wouldn't be that light anymore. This is a facade bracket, so in the architecture example, so you've got 4 sheets of glass coming there. So the approach we're now looking at, that we're going to implement and inspire as of yesterday, design and non-designable regions. So you've got your grey non-designable, turn the entire designable region into lattice, and not the mixed one we saw on that Renishaw example, but on this example, so all the solid regions remain solid, and all the lattice regions become 100% lattice, if that lattice is optimized. And pretty much everyone that sees these thinks they're aesthetically a bit more pleasing than that kind of mix of lattice and solid. So that's the approach we're taking at the moment. We might change it depending on feedback. But again, some really nice looking structures. That again, that could have a thin skin on it if you didn't want the lattice exposed. You get the thin skin on it, print lattice inside it, get the best of both worlds. This was originally done by our Italian office. I redid it in Inspire as the Ducati Monster motorbike. So again, things like motorbikes, bikes, quite a lot of furniture. You know, the design codes specify the loads that go into them. So they, in some ways, they can be quite easy to set up the model. Again, you still get to choose the kind of original aesthetic layout. So again, this was to demonstrate Inspire plus the Pioneers modeling as well. And a lot of these renderings are done in solidThinking Evolve. I'm not an expert user at all, but I've learned how to render because I like the pictures. This is more typical from the my engineering background as an upright and a former SAE car. So again, you've got that braking and cornering loads, measurement, or just well-defined tests, split draw direction to allow for machining. Again, same weight, but it's like 2 times stiffer and no stresses allowed. So better performance for the same weight or cost is also another thing that you often get. Really nice design. Some more architectural stuff. So Luca is one of our colleagues. He's been mentioned a few times. I've worked with him on a few projects. He wanted to kind of replicate the type of things you see in some of the nice architectural designs. So I had a crack with Inspire to, I'm not trying to duplicate it, but just show its use as a thinking tool. So I divided the tower up into the bottom part, the middle part, and the top part. Each one of them, you can just about see the rotational symmetry planes. I had different numbers of symmetrical planes on each layer. I did some wind loading and a pseudo-seismic load on them, and got this very latticey structure. Then used a few tricks to put a solid structure on the inside to get a decent rendering. So these diagram kind of structures in architecture are apparently quite popular at the moment. So that was what I learned a few years ago. That's one of the things we're trying to replicate. So this is the Auckland City skyline. We've got a standard telecoms tower that you can go up the top of. I think they look very boring. Every city in the world that wants to give you a view's got one. So again, just using that same process with Inspire, generated a shape, rendered it in Evolve, plug it back into the skyline to mask the old tower. So no one's done it yet. Maybe one more. I could be famous. This was just an idea of a pavilion study. So imagine sort of a superstructure with kind of glass filling in. Again, that just started off as a very simple dome structure with wind loadings and gravity loadings on it, which came up with that, with the kind of white frame, and then just sketched over the polymeres. Again, the whole process probably took an hour. So just a thinking tool. You can change, I mentioned the minimum dimension of things. You get very different designs as that changes. So you can play with lots of ideas and come up with cool concepts. So again, Luke is always hassling me with running architectural models on all the latest functionality we have. So I ran that through the lattice approach the other day. Now I know, so some of these architectural things where you get the structural members come together in all the different nodes, and if you've got these very curvy buildings, and you might have 5,000 different nodes in the building, and everyone's got a slightly different geometry. So again, that leads itself to 3D printing. Also leads to the voxel jet type approach where you print the sand to then cast all your individual nodes. So you get something like this. Could be, you know, every joint in that could be different. It's different thickness beams coming in, but you can potentially, in the past you couldn't even conceive of manufacturing it, whereas with 3D printing it does become possible. So it's just a close up, so you can see again it puts the thick members where you need them. It reduces thin ones down. You can see they're tapered. There's a good example of a tapered one. So again, for what you've got an optimum structure, not just a conformally mapped structure. Next is one of my favourites. I've seen the RMIT in Melbourne, so it's a fairly famous university. It has a very, very good design course, and so I helped one semester. The students had to use Evolve and Inspire to design a piece of furniture. So this Elliot Mackey did this. So built the design space, built Inspire, put the loads on. I don't have those images, but that was his interpretation. So it's very organic. We can share. The next thing he did, which was brilliant, is he managed to actually get that into solidThinking, I think it was, with a full detailed CAD, full building materials. So perfect bit of engineering. That could now be manufactured, printed, riveted, whatever. And again, I don't know if you've seen Evolve, but very powerful rendering, so you can put it into different environments. And just imagine yourself sitting in the designing chair in the study room. So it's very, second year student, fantastic piece of work. More bikes. So again, I'm a bike guy. This was done a couple of years ago in Inspire. Sketching over the polymers, the whole process becomes very, very quick. You go, well, does it work with composites? Well, Inspire tells you where to put the material, what you do with it, then different design approach. Again, a thinking tool. You might do it differently if you're going to make it in composites, if you're going to make it in extruded aluminium, if you're going to 3D print it in titanium. So it gives you that starting point. You don't have to use the results literally. You use them as an inspiration for something new. I probably don't need to talk too much about the robot bike. We've seen it a bit. But again, each node, again, very like an architectural node, you're joining these carbon members into a point, and for every different person, that's going to be a slightly different angle. You can 3D print it, so customizable and flexible. Saw my little lever example before. That didn't come out of nowhere. It was actually Raceface, one of our very first Inspire customers, with this mountain crankset. And again, you can see their design down the bottom left is not dissimilar to that lever. So it's quite interesting. You see stuff that's been built the same way for years and years and years, and then you go and throw Inspire at it, and stuff comes out looking different. And yeah, it's eye-opening. The Empire bike that when Shaw printed, the Inspire was actually used on this piece up the back here to optimise the shape. Bit of heavy engineering. These are control arms on truck axles, and I can't remember the number. It's something like 15 kgs per one of these, and there's at least 4 on every truck. So straight away you're saving 60 kgs on a track, which you can then carry as payload. So weight reduction in heavy transports really important. That piston was actually done by a friend of mine in Melbourne. So 300Z, and this is 300Z he wanted custom pistons for. So I actually helped him set that up, and he got a good weight reduction. He also had a material change. He was going to 3D printed titanium, not the original aluminium. So again, change material, do optimization, you get a different looking design sometimes. So I just have to read it. I've got some videos that I'm not sure I've actually ever run through them all. It goes through the kind of the full process from start to finish. So I think it's probably just to kind of nail it in. It's probably well worth doing. So again, mountain bike guy. This is that suspension pivot up in the corner there. And see if my videos start. Yes. So the very first thing to do is you put your loads and supports on your structure. So you see the little red bits have arrived. That's like a pivot. There's some forces in there as well. You hit the analysis button, and very quickly you can start looking at results. And if you've got CAD data, you can just drag and drop it into your Inspire window. There's only 3 or 4 little icons at the top you need to learn to use at the very beginning. You can put your loads on and really quickly just analyse your model and find out how it's performing. And that's just looping around, so that's good. So again, running the model takes a couple of minutes, you get answers. Next stage is developing the design space. So that initial model was, had the pockets in, might have had the ribs in that lever example I had. So what the next stage could be is to go back and remove all those features that they're design assumptions. You want to get rid of them. You want to back off to get more of the package space. These are partition tools. So again, when people do CAD, you're not normally dividing a part up into where my loads are going to be, where my supports are going to be. You just have up part. So we've got various tools in Inspire to help you break the model up. So now you've got these grey non-design regions with your loads and supports, and then the designable region. That's good, but you've still got all those initial assumptions. It's better if you've got more package space. So again, if you've got a design at the beginning of your process that you've got the maximum package space that still doesn't meet your design targets, it's good to know that early on. You can go back and, especially in automotive, you can argue, I need more space for my bracket, otherwise it's never going to meet your targets. So this is, as much as possible, you build up and use as much design space as you possibly can. So that's, within your package, that's potentially everything that's available to do your optimization on. And once you've got that, again, your loads are still in your model there. This is setting up a symmetry constraint. So again, very simple graphical representation of stuff. No complicated menus to learn. Everything's just up there in the little icons on the top. Run it again. Do design exploration. Look at it using different amounts of material. Look at it using different stress constraints. You can change your package space, and you can hopefully. My video's quick. Load the results. See, it doesn't. These results are often quite non-intuitive. So I mean, again, Armin showed the rib on the Airbus wing. I worked on a wing flap once, and we had 230 load cases in total, which we filtered down to about 70. It's very hard to intuitively, as a designer and engineer, know how to trade off those 70 plus load cases, and that's what one of the big advantages of the optimization is. It does that for you. And then you can compare your multiple concepts. So down the bottom there, you can run many of these iterations. We've got these tools. You can compare the mass displacement just in this little table across the bottom. So really quickly go and drill into what are the best design, best options. one of them might perform better, but you think it looks terrible. So you go for the one that looks better maybe. And then this is the one-click reanalysis. You've got your result, and it really is this simple. You change the threshold, hit this little analysis button, and you'll get an answer. And change the threshold, run it again. And that was actually real time, I think. So that's how quickly it runs. If you do it on these computers, they might be a bit slow. So again, different concepts, maybe using different manufacturing methods. No constraints, draw direction, symmetry, no symmetry. So you just really quickly run through and check all your concepts and find out which ones work for you. So that's use it as a thinking tool. It's not that answer. It's a really cool way to get to something interesting.
Sorry.
Yeah.
Do you mean that this type of software can do the structural analysis?
Yeah. Okay. Yep.
When you have input the loads, directions, and the magnitudes?
Build the load cases up and frequency.
Even the gravity.
Got gravity, we've got thermal loading.
But at the same time, you work with engineer like software engineers. You can analyze the load for this model.
Yeah.
Do you work with like software engineer to get that load correct?
Getting the loads.
No, that comes out of the
Do
MBD.
you need
Well,
to?
with the MBD, in this case, the loads come from the motion type analysis, but you still need to have your spring rates and the size of the rider, and so I think when you do analysis, it's really easy, except you don't know your material properties, and you don't know your loads, and that is the hard part, is getting really accurate information to put in, which makes it even more important that you optimise, because you've got a good starting point, and you get more robust designs that are more tolerant to getting that stuff wrong.
Actually, you input the material properties to get the load correct.
Yeah, I think I will run through it real quick, as long as I've got enough resolution. I'll try and run start to finish through something in like 5 minutes, without skipping it. So this is the polymers sketching. So again, really quick tools for setting up just a visual section. So I'm only looking at half the model, just makes it easier to do my sketching. You're just going in, it's called a wrap, so it wraps around the existing results. Where our kind of holy grail at the moment, the place we want to be is click one button and automatically wrap the whole thing. That's what we want to do. If we can do that, it'll be pretty awesome. But this is, you create them, you can then pull them around, you can resize them, translate all the various parts of your polymer. I might fast forward through this one. 5 minutes later, you've got something that's looking pretty good. You still have to do some detailing, where your polymers join into your kind of regular prismatic kind of structures. You need to perform Boolean operations and put fillets around the corners and Boolean, that's the Boolean together. I think I'll do some filleting now. So again, to do this in a regular CAD tool would be very difficult for those organic shapes. So again, we're adding a lot of stuff to Inspire to allow that to be even more efficient. So again, you've got your final design. All the loads and constraints are still on there. Your HIB analysis again. Again, this is almost not quite real time, but almost. Got the results, load them up. So again, in Inspire, it's all your analysis and your optimization. The optimization is based on FEA in the background.
I mean, load is one thing, but for a component which is subject to all this dynamic movement, I think wear and tear is another important consideration, isn't it? And how do you address this? If it's a moving part, I mean, there's an axle which comes into direct friction with it, and so on. the material will wear away, isn't it?
Yeah, I think it's. I mean, if it's fatigue analysis, we don't do that in Inspire, but we can do fatigue analysis when you have a load case where, in stress threshold, your ultimate life on the SN curve or something is a constraint. You can set a stress constraint up, so your optimization will keep your stress below that in your load case. So actual wear and tear, that's a dark art in the simulation world anyway. There's not a lot of simulation models that actually model that kind of.
So that is very specific what you mentioned to be simulated. So do you have a case?
No, I'm just looking at your device, which must have a lot of axles to go through the holes and so on, and it moves. I mean,
it's got bearings in there, so it's press fit bearings. So the bearings wear out, but that shouldn't wear out.
All right.
So you do not have surface to surface contact. Finally, here you assume that the bearings inside the holes are rigid, and they cover all these relative motions, and these are how do you call ball bearings and all that stuff, or whatever bearings they are, and you do not consider this. I think that companies like INA, that's a German company who built these bearings itself, they look into that in more details. But I think for this kind of a simulation, you need a very specific method to do so.
All right.
And in the real world, on my mountain bike, I have to replace those bearings every 1 or 2 years, or replace the bike because they get sand in and they wear out. And so yeah,
Right.
So they do wear out, but it's not the part; it's the bearing. So you've got that nice result. You're happy that's working. So your nice polynerve structure, that one there, we can save that as an STL file, which can go straight into Cura or whatever the pre-process of it, the 3D printing machines are using. That's just a rendering, but that's, again, it's rendered in Inspire, so it could theoretically have just gone to the printer, been printed out. Again, because I've been testing lattice, I thought I'd latticify it. So again, I took that, did that optimization, got the result. There's a product called 3matic, which I read the result from Inspire into directly. So they're just beam elements, and it can turn those tapered beam elements into an STL file. Again, that was very hard work on my laptop. That was the resulting file, so I couldn't actually bring the result of that into CUDA. It was too big, so this was just a simplified version just to show it. So again, lattice into 3matic at the moment. We'd like to be able to create those STLs on the lattice structures ourselves, and then in that tool you build up your ready to print model. So here our circle of life now, I've called this the circle of life for years. It's like every stage. The very first one, you get your existing design, you confirm it works. If you don't know your loads, but you've got a part that you know works, you can just put unit loads on, measure those responses and use those as your target for your optimized design. That's what a lot of customers do. Existing design, package space, optimized design, print, pre-processing, finally print. So we need more spaces in our circle of life printing stuff. So I had on my original agenda to do a workshop example now. I don't know how we are for time, if I should just run through manually the process from start to finish without any magic. I think we can fit that in. Be maybe 10 minutes if I do that.
What is the timing for? Is it lunchtime yet? No.
Lunch time is 12:30, according to this.
Yeah, I think it's good. Yeah, I think it's good. I just have to make some space for this. Just a really simple example.
simulate 即係嗰個 optimization， 佢係 powerful 要搞多啲嘢啫，冇所謂嘅。其實我想
very high resolution. It's going to be interesting. So all of you have got Inspire installed on your machines, I think. This is a slightly newer version. And you've got, and I'll just run through the whole process from a blank sheet to, so sketching tools up the top here. I'm just going to sketch a rectangle. I'm going to put some circles on it. So you can Control Z. Control Z lets you undo everything. Right. Now I've got this push model. So we've got something called direct modeling where you can just start dragging geometry, doing crazy stuff to it. We've also got, and this is really cool, you can actually pick features and move them around your model, which is kind of crazy if you can do that stuff. And that works on any feature, beads, all kinds of stuff. I don't want that to be quite as thick as a paper. I want a partition, so again I want this design to be both design and non-design regions. So I pickle those, partition them 3 mil. Yeah, no, my manufacturing says it needs to be at least 5 mil thick. Partitioned. And you see on the left there I've got different parts. I've got some graphics issues here without doing that. Is that right again? I can right click on that and say that's going to be my design space. That's going to be my designable region. I want to put loads on this model, so I go to structures. I can put straights on the holes. Again, it's all very graphic. I can double click that. That means it rotates about, pivots about that point. I can put a force into this hole and say how big it is, maybe 2,222 newtons, in which direction, Y direction. So let's pretend I hadn't made that design space yet. I can just skip a bit. Everything by default is given a material of steel. We provide a material library. You can put your own material information in there. So I just go with defaults. If I hit run, keep everything big, make it fast at the moment. We do proper non-linear contact if you want, so proper opening and closing contacts. Just won't use it, slows it down. I can run that. So this is just using it as a finite element analysis tool. I've built a model. I could have brought that CAD in and edited the CAD. We support pretty much everything. Bring it in, run an analysis. At the moment it's meshing, which gives me a chance to stop talking. and sort of introduced Altair in our software. So we've got a suite of software called HyperWorks, which I think is now close to 50 different bits of software. And we've got 2 or 3 different meshing tools. One's called HyperMesh, one's called SimLab. So in the background of Inspire, we're launching HyperMesh or SimLab in a batch mode. So this is, you know, our 30 years of engineering expertise, kind of doing that work in the background. So you don't need to be a CAE expert to use it. So when that's run, double click on it. So I've got, you know, my proper FE model, displacements, stresses, nice interrogation tools. Where are my hotspots? Very easy to use. It's quick to get to. So we're happy with that. We can turn that into design space now. Now run an optimization. So we want to do topology. I mentioned topography gauge. You can combine topography and gauge together. And there's lattice in there now. So we'll just do topology. One thing I didn't do, I wanted to show you the shape controls. So I'll do an extrusion constraint on that guy there. So that'll just be, the result will be a constant section. So it's actually cheating a bit. It makes it much easier for me to do the polynavs on top. So that's why I do it. You can see split draw, single draw, the topography controls, the symmetry controls. So now I can run it. I'll do topology. I can minimize mass and put stress constraints with a safety factor on, or because I'm just using arbitrary loads, I'll just maximize the stiffness using 25% of material. And here's that minimum dimension size. I want a nice, good chunky members to make my sketching easier. So I'll now run that. So again, in the background, it's using SimLab to build the mesh. Once the mesh is built, it writes an OptiStruct file, which is our very advanced FEA solver and optimization tool. And we'll then launch that. When it's finished, we can get the results into Inspire format and read them back in. So what would have taken lots of manual work not so many years ago is now pretty automated.
So in the background, actually I showed a lot of examples in automotive and aerospace where we have a lot of things to be considered. Crash loads and stiffness loads and fatigue loads and whatever. So this code OptiStruct, that's actually the name of the tool, developed since 25 whatever years, more, maybe
23
years. That is a collection about of a lot of functionalities, and that is actually running underneath the surface. You don't get access to all the features through this Inspire tool, because it's a tool for you to use it in an easy way. If you want to, it is possible to export and go into these, I don't want to say an expert tools, but in tools where you have a lot more opportunities to guide the optimization. But that is only if you really want to do that. And our goal is to package the functionalities in that way that you do not need to do that.
So that's run. So again, the optimization is an iterative process, so it probably ran 20 to 40 iterations. So it's total solves each time. So again, it's pretty efficient. But again, it's run. So I double click on that result. So there is the it's the topology result. As I kind of mentioned, you could look at the different thresholds, way up here, way down there. I can do an analysis on that. So again, in the background, building a mesh based on that, and we'll run it. This file, yeah. Well, you can also make this file.
I know, but it's relative because you're not going to try it. Do you want us to try?
No, this is Well, no, we've got a proper tutorial later. So there's a more, this was just trying to get the whole process tied together. I'm happy to share this. So again, here's the result of that. We could have also gone back to the results and done an analysis maybe at that level. You can compare how the different ones perform. Again, I want this to be really simple to sketch over. Conscious of time. So I'm going to use that and go into the polynerves to try and demonstrate that for you. So go into geometry, polynerves. To prove it wasn't a trick before, I can just start sketching over my structure. I've done a few of these now, so I'm getting quite fast. And this wrap tool does 9% of what I normally want to do. And just doing this with conventional CAD is virtually impossible. Surface, that edge down. Just press the wrong button. If I wasn't pressed the time, I might do this a little bit differently. As quickly as possible. That looks pretty close. I'll now go in the Boolean, turn the original part off. I can subtract. That can be my target. These can be my tools. The nice thing about doing that partitioning is all those loads that were on those non-design bosses, they stay there after I've finished this. See, I've got these little leftover bits in here I want to delete. So there is, if I go into structure, I could boolean those back together and do the fillets and stuff around the corners, but I won't. So yeah, I've got my final design. I like that. Goes to showing contacts. I can run a conformational analysis on that. Actually, I need to do something else first. So as long as I didn't do anything wrong, that's pretty much the whole process from design space and loads, concepts, final design. It looks. What can be wrong? Geometry, slightly overlapping.
Can you show me one example which is incorrect?
Once this is run, I'll mess the model up and show you. It's not incorrect design so much as things that can happen when you're using software that go wrong.
And then you put with the software vision mechanism to self-track all those
Wherever possible, yeah. So I'll break this in a second and show you. So there's our results. There's our final design. You can measure displacements at points. We can so different result types we can look at. We can show show reaction forces at attachment points. So lots of really, really nice design stuff in there. So to answer this question, what sort of things can go wrong? For example, if I move that to there, so it's just overlapping a little bit, I'll make it overlap a bit more. When I try and run that, because that's not real, that's bad geometry. If I try and run that, I should get a warning that the two parts overlap, and it tells you what the parts are. It's already struggling, it should have completed this more quickly. So it says, okay, intersecting parts found, it tells you to go and fix them. So we try, it's one of the philosophies behind Inspire, is we try and catch all that stuff and give good information. And if you've just done something stupid like that, I can Control Z, I can undo everything. It should be fixed. So that was my quick example. So we could either get the class to do it in half an hour.
Can I have some questions?
Yeah, of course. Go ahead.
What's the margin of safety in your design? I mean, because this is just a software, right?
It's just a software,
yeah,
right?
Yeah. What is percentage, the risk factor? Like, it can be wrong. And
So,
also, how, in terms of by structural loading, you have a margin of safety. What is this margin of safety?
Well, these are the points which can go wrong. Actually, you have to specify the loads, the accuracy of the loads. That is important on the one hand, and the stress target. What can the material sustain? That's and you have to bring both together.
Yeah, but in your design, you must because this is one of the tools to achieve the ends, right? So in your design of this software, what are the factors the basic assumptions that we have to assess the risk factors at the end, right? Like engineers.
Well, no, I think the user makes those assumptions, the software. So this factor of safety, we can plot the factor of safety at the end, but that's just the stress over the allowable stress. It's only the other way around.
Yeah, it's just a hand calculation.
It's no different to doing a hand calculation or a spreadsheet. It's an answer. It really depends on the question that you've asked it.
So at the beginning, as every engineer, you have to define the allowable stresses, and our software will guarantee that you will not reach these allowable stresses or overshoot these allowable stresses based on the load case that you have defined. So finally, what can go wrong is that you see an overload because something happens. I bought a bike and then Tony is, had a good breakfast and sitting on the bike, and the loads are higher and they reach this stress target, or the material manufacturer is giving you a different material and you assume that's the original material. So there are a lot of things that can go wrong in the whole process. What we do and what our job and the job of the software is, we bring the loads and the target in terms of stresses, displacement, stiffness together.
But in some calculations, you do have some buts, right? Somewhere out there. Because it seems so perfect in your presentation. Because like in certain computers and calculations, you must have assumed certain risks, or in case this happens, what is the risk in case this happens? What is the risk of this? Because it's different from manual calculation.
It's not a manual, it's not an analytical calculation, it is a finite element calculation. And finite elements have different characteristics. You can have the element size can be larger and smaller, the type of element that you have, the type of mathematic approach which is behind the element.
there are different possibilities, and I mean a scientist can work a lot and getting slightly different results based on different mathematical approaches in the background. When you use the HyperWorks suite, where we get access to a lot of these possibilities to change these approaches in the background, you can do some research on that. And I think, I don't know exactly how we do that. Oh, you see the elements here. Yeah. In Inspire, we try to bring the best approach to the user. And we do some assumptions on that.
Is it possible that this result I use on other software? It is something wrong. I mean the same result, can it be tested with different software and the result is the same?
It could model on all CAE or all FEA tools. If it's Nastran, Abacus, Ansys, HyperWorks, the same model these days, I think they all give a good consistent answers. There's very little difference between them.
So you will get, I mean, what means an answer? Maybe that digit might be different, and that point will maybe sit here and not here, and the size a little bit different. But I want to say, what design decision will you do based on these results? And what Tony said, these results will all be in the same range, that you will derive the same assumptions or design decisions later on. So this software will give you a slightly different result, maybe, but it is in a range, in a tolerance range, that should not influence your design decisions.
And will be better for that example than the hand calculation.
Because that is not possible to do a hand calculation.
It's not possible to do a hand calculation without running.
Maybe not my generation anymore, I would say. So.
Do you mean like if we do?
Is there any way we can verify whether the design is technically competent?
With 3D printing, you can then print that and test it very quickly.
Yeah, you print it, you test it, you put a stress gauge
what
on
other
that.
verification method we can adopt before we send a print using 3D printing to proceed the printing?
Straight agent?
I mean, before you print it, okay, a physical test, for a physical test you have to have a physical part, so you have to print it for a physical test. So for a computer-based test, it's what I said, a lot of, in the one graph, a lot of certification tests, or it is going on, and a lot of tests for vehicle certifications or aircraft certifications, they go into the virtual world now. But therefore, it's exactly what you said. You have to define the methods, you have to define the right material properties, the right loads, and then you have to do it one time and verify that this process will lead to the right answer. The methods are quite good already, so the risk that you get a wrong answer is low, but still having one time test, and even 3D printing is not always printed with the same results, but having a test one time to verify the process, it's something that you can do. So engage on top of it. And then in the range of this part and the usage of these parts, you can be sure that the result will be maybe not 100%, but a 99%.
You find a lot of the large automotive companies like Ford, they have their own very clearly defined processes for how you build these models. So they define what your element size should be, define how you should model your connections, your welds. So that's all very clear. And they've spent years verifying that, so And we try and LT has done that as well. So that's what we try and put into Inspire, is all those rules that we have for building a good quality model. I mean, I can get very different answers on that model by refining the mesh size.
It is, yeah. That's the point. It is possible you influence the result, but the answer, the design decision finally, whether that will meet the target or not, that is more or less same for different softwares and slightly different.
We now have a 3D printer actually can print this component into alloys, such that we can test the material instead of plastic.
Yes.
Yes.
But I mean, when you print that and bring that into reality, you have to know what the printed material will look like and what that can withstand. It is different to a forged aluminium, for example, and therefore you have to adjust your targets of the stresses.
And that can get really complicated because your print direction changes your material properties. So this part might not work if printed in one direction, but could work if printed in the other direction.
So all the materials specified under this software, like titanium.
Yeah, but there are a lot of titaniums possible.
They got TI-17 or 6211.
They're just generic values. They're not.
So they are not actually material.
They're from the metal. They'll be from the metals handbook or somewhere. But every 3D printed material will be different.
It gives you. There is a material out there in the world which 100% fits to that value. But there is a lot of variants possible. When you go to a plastic manufacturer, I was at one chemistry customer, and they have thousands of variants.
For designing material using
Well, that stress is the same pretty much no matter what material I use. You can then look at that stress and choose your material based on the stress level. So you might choose your grade of aluminium or your grade of steel, because the stress will be the same. Close.
Sorry, did you mention that the capability of this component will also depends on the direction of printing?
Yes. Yes.
Is it a bit pattern? The bit pattern, can you circle radio?
Yeah. The 3D printed, the directional printing, and the heat treatment, it's all in there.
That's why I had in my slide, I mean, just to buy a printer and start printing is not yet the end of the story, and that's why, for example, the Airbus guys, they put all the effort and investment into it to understand what is influencing finally the behavior. Printing direction, material properties, material treatment, before printing, after printing, and so on and so on.
But I suppose the direction of printing is a well defaulted thing. So can you incorporate that into the software? I mean, just to choose which direction of printing in your software for analysis.
We don't have directional material properties in Inspire. You could do it in Optistrap.
Yeah.
You could.
Yeah.
So you could actually, you could probably do an optimization on material. What's your best print direction?
Yeah.
I think you could do that.
Yeah, we do that because that is like a composite material has directional properties depending on the direction. And we do, that's our standard use case, we do direction optimization, what direction is the optimal direction. And as well the optimal combination about different directions.
So of course the beauty of such software is to tie up with the 3D printing.
It is possible, but but I think it will need some investment in building up this workflow and method that actually we have not yet done. But it's possible, yeah, we can do.
No, you know, some of the metal printing processes, there's not much difference in the properties, directional properties. I know some of the plastic ones, that strength can be 4 or 5 times different from one direction to the other. So it becomes very important.
Yeah.
I myself is a bike lover, so I myself is a bike lover, and bicycle, and it's very popular nowadays. We are using carbon bikes.
Yeah.
So you know how carbon bike is actually manufactured. It is very tedious working this layer of this carbon material. So do you think in future or now 3D printing can help to improve or to replace this so many manual jobs, say in China or in Taiwan, that they are performing?
I would not say it's 3D printing, it's 3D patch layered ring. And we had 3 years back, I had a bike saddle optimization where actually a manufacturing tool maker, they had a process to place small patches of different angles by a robot, and we helped him to optimize a carbon saddle, what patch, in what direction, with how many layers, and so on. That was our job, to optimize that, and then the machine is putting that one after the other, and then the raising comes and it's done. So even 50 grams or 20 grams lighter than standard carbon saddle. So I don't know, when I'm honest, I don't know how much manual work is there right now, but I'm pretty sure that will be automated in the future. But I don't think it's a printing. You don't print the fiber, I would say.
I have seen robotic fiber laying down as well.
Yeah,
fiber and weaving and robots.
I mean, when I was in university, we had some research working how to place the fiber around and stitch it and so on. So we do a lot of carbon bike optimization. There's a lot of things going on, but I don't know exactly how they manufacture it later on. I think it's manual then.
Can I ask, for manufactured product in industry, how do you QC the quality control of the product? You don't print out everything is the same, right? How do you test the product is what you want?
The one example that I had with the bracket that goes to space, you do it 2 times, and then you hope that left one is exactly like the right one.
You don't only hope that.
Then you X-ray for defects.
X-ray
for defects.
Yeah.
Oh, but you're checking whether there are some internal defects within the material. How about in the dimension?
It's no different for 3D printing as traditional methods. So my master's was in cast rolling wheels. So we would X-ray every 50th wheel or just to check.
You do load testing?
Yep. And so every wheel is visually inspected, every 100th wheel was X-rayed, every 1000th wheel went onto a test rig, something like that. Sampling. So,
and I mean, there are some parts in the automotive or in the aerospace industry where you have 100% test. X-ray test, I mean, not destroying test, of course. You're not allowed to influence, bring some pre-damage into the part. You have to ensure that, and therefore X-ray is one good idea. And the other thing is, I mean, quality control. You have to certify your manufacturing process and the material, what you get from the supplier, and 3D printing machine. All the parameters have to be adjusted and have to be controlled, that you have a repeating process. Room temperature. There are a lot of parameters influence final result. And it all depends on in what tolerances you want to go. When it is just a household part or a small toy which is cost $1 or $2, you will not put that everything. Or an aircraft engine fuel nozzle, I'm pretty sure they have 100% test.
Turbine blades.
Yeah.
Main landing gear strut.
Yeah. So that is different. And is your question somehow answered? Oh, thumbs up. That's good. So. Yeah, the screensaver all day. So other questions?
So,
Whatever you have in your mind.
So basically,
what do you mean? Because we had a 2D problem at the beginning, you mean? Or by
this gentleman just shared, is that the topic is converting 2D to 3D?
No, I just sketched a simple part, just to be.
But now it's from 2D to 3D.
Ah, okay. I think that question should go to Christine. Because these are.
So it will not be coming today.
So if you wanted to print this,
yeah. Let me.
I can right click. I can file, save as STL. I can save that. So this, I don't really know how to use this that well. There is that part inside Cura Ultimaker that could then be set up for, you can prepare it for 3D printing, with the paths, the print direction, that can all be set up there. So from Inspire, you can export the STL file, take that into your 3D printing software, prepare it for printing, and more launch the print process. This is, Altair stops at this point. We don't really have much expertise beyond your fucking. We have other experts in the house. Whatever works.
大家唔介意嘅話，用翻廣東話講好嘛？咁呢一個 program 咧，其實就叫 Cura， 亦都係佢哋嘅產品嚟嘅。呢個係臨入去 3D printer， 即係將個 file 入 3D printer 之前用嘅。咁佢個作用咧，就係將你嗰個 file， 即係譬如頭先我哋喺 Inspire 畫完晒所有嘢啦。咁跟住我哋就攞到一個 STL 嘅 file， 咁我哋就會擺入去個 Cura 嘅 program。咁佢咧個 program 就會自動去分析翻個斷層嗰度個 thickness layer 咧，你要 set 翻，譬如你部機嗰個 spec 個嘴頭佢 print 到係0.2 mm 嘅個 layer thickness， 咁你要入翻譬如個速度啦，你想部機個嘴頭行嘅速度啦。個 layer thickness 要幾厚啦，咁佢咧就會自動幫你 gen 個叫 G 曲嘅file， 咁佢亦都會 show 到需時要幾耐嘅大概，係啦。咁喺呢個program 入邊咧，譬如你而家見到佢係打橫瞓低咗嘅，你如果想打直咁樣印咧都可以，但係變咗個時間一定會係長啲嘅。因為基本上一個即係 even 同一個 size 啦，你 3D printer 咧，你個厚度或者成件object 嘅高度越矮的話，佢 print 嘅速度會係越快嘅，成件碟，因為佢將個 reset 做佢再褪落啲嘅時候咧， 佢個需時會耐少少嘅。
但係其實係咪話個 printer 都會唔同嘅？頭先佢都話好多種 printing 方法㗎嘛。
其實佢係有4種技術。
係咯，係咪每一種都係2Z越短越好？
正常係啊，因為佢個基本上咁多種嘅4種技術啦，佢嗰個2Z軸嘅移動都係會比較慢少少嘅，即係佢都係逐層吞落去嘅。講緊咁，所以如果你將嗰個褪嗰個程序減少的話咧，就會比較快啲嘅。即係 even 就算同一個object 都好。同一個 design 都好，同埋其實咁樣print 出嚟嘅話，假如我哋用緊一個 FDM 嘅 printer， 類似係呢一部咁樣啦。咁如果係咁嘅話咧，佢個 support 嘅 materials 咧就會比較少啲嘅。咁咩叫 supporting materials 咧？下半集我會再同大家講一講嘅。係，因為我哋都預備咗少少 sample 係俾大家去試下點樣拆個 support。咁亦有嗰個成件物件喺手嘅話，大家會了解得更加清楚啲嘅。
即係晏晝會講，睇下晏晝會講。
我想問下咧，呢個工學咧，佢 support 邊啲片係咪咁多種？即係市面上多種片頭？
基本上市面上咁多種都會有㗎啦，除非佢嗰間公司即係自己整一個 program 話，我哋部機淨係可以收呢個 program 嘅啫咁樣。係啦，但係大部分譬如 Stratus 啊、3D System 啊嗰啲機咧，其實基本上都可以用翻 Cura 去 gen 個 G 曲，因為你最想要嘅係個 G 曲。你有個 G 曲嗰個 file 咧，你擺落個 SD 卡度或者 USB 咧，你插翻落去個 3D printer， 佢會揀翻個 file， 佢會識得自己揾自己開始編㗎啦。
我想請問晏晝我哋會講邊4種 3D printer？ 我哋晏晝會唔會講？
我會簡單介紹一下嗰4隻嘅技術咯，係啦。
因為4隻技術嗰個support 都有唔同，拆嘅方法都唔同。我哋今日會教大家拆嘅係 FDM 嘅技術嘅support， 即係有喺手嘅，大家會攞得上手，同埋會試下點樣拆嘅就係 FDM。但係另外如果3種咧，就因為個 cost 同埋部機都好貴嘅，咁就大家我會播啲片俾大家睇，同埋有好多係嗰啲太多 chemical 嘅嘢，我哋都唔想俾大家點。
其實而家好多 3D drawing 嘅，比如話即係喺 3D industry 有叫 BIM 啦、BIM 啦，咁其實可唔可以用 BIM 就 convert 呢個 color 再 print 出嚟？
轉翻 STL 得㗎。
你 output 即係我 BIM， 即係 BIM 嘅 file 轉咗 S， 即係
你 output 你 save 嗰陣時，你 output 嗰陣時 save 做STL 或者叫做 STEP， 咁佢都可以就入 Cura 呢一個 program。
即係好多個 3D drawing 嘅 method，
基本上可以
轉咗，即係同嗰個轉 Excel 咁樣，即係轉咗第二個 format， 經過呢個 Cura 就可以變係咪咁啊？
比較貼切嘅形容應該係 Word 轉 PDF。
係，即係類似，即係轉個花方咪就可以啦。
係啦，
即係唔一定用 Inspire 去畫嘅 ，Inspire 其中一種。
其實好多種畫 3D 圖畫 CAD 都可以。我哋叫 CAD 啦 ，Computer Aided Design 啦，都可以將翻做 STL 嘅包。
Inspire 只不過係可以做啲 manufacturing 加埋 loading 嘅。
佢哋係啦，做啲 analysis 即係因為你有好多純畫圖嘅 program analysis 嗰方面係未必比較好嘅。咁即係因為我自己都係 engineer 啦，咁有兩隻 program 我自己都覺得，譬如畫圖係用呢一隻好啲，但係分析咧我就要用翻呢一個 file 擺落去呢個 program 做分析會比較好啲咁樣咯。即係有個compare 喺度嘅。咁基本上你畫圖用乜嘢其他 3D 圖嘅 program 畫咧？你用翻 Inspire， 即係轉咗做 STL file 先啦，跟住再轉翻做用 Inspire 嗰個做啲 analysis 咧會比較好啲嘅。
其實香港用呢啲有幾多嘅？記得 Inspire 有幾多人用 Inspire， 或者呢一類嘅 program？
比較多係啲 designer 會用，
The manufacturing.
Is it possible to catch up a little bit about the discussion, because we just hear the word inspire and STL and we were wondering about what.
I just briefly introduced the
We are not
Quora
saying
today,
bad things
and
now.
then a little bit about 3D printing to them, and they're just wondering that how many users need to like inspire with it in their industry.
Okay.
Yeah. So.
And that was as well about the formats. So we can export a lot of different types geometry formats. I think that was as well a little bit the discussion about.
Yeah, because they need to know that every different 3D program that they can use it back to
Okay.
So basically we can read pretty much every CAD format, so and then we can export enough.
So to read in, it's mainly for the design space, and therefore we read that in and then run it, export STL.
Mainly, you have the STL file, and then you can use the Inspire Enter, right?
Yeah. So I know it's lunchtime, so I will make it quick. So I'm Lawrence. Thank you for the presentation. It's very inspiring. Just have one very quick question. So I see that there's enormous potential for the program to be used for like bicycle, small parts. But to me, it's almost what you have shown so far is mainly to do with structure, how to optimize the structure. And I can see that you can also do a lattice analysis, which to me, as an architect, I think of boring, like opening holes in the structure, which is essential to us because we always need to open windows, do environmental analysis, like ventilation, sunlight, etc., etc. So in that sense, that relates very much to me. But what I see, how I can use the program is that for us as an architect, we always want to analyze, for example, analyze the structure, analyze the behavior. When our design comes into how does it respond to the criteria that we have been given. And we always use programs like Revit and Rhino, and we generate a nerve model, surface model. So actually, is it possible for us to import or export our Rhino model, for example, into the Inspire program and then run the structural analysis as you just did?
It should be, yeah. Yeah, on Rhino you can save in step, and I think Evolve reads the Rhino format directly as well. Yeah. So yeah, definitely there's definitely a way to get it over.
And then use that as just an analyze tool. You want to do that? Okay.
But I've seen some structure stuff where you take windows out or whatever, and then you put your loads on, and because you've got these strange shapes that you have to get around, then you'll find out where you can put your main structural members. It can help that thinking process really early on. But just simplified loads as well. You don't have to get carried away. Just the loads that define the main members, and in automotive we've got it down to not too many loads just to get the main stuff out.
I'm interested to follow up with this question, the scale of your analysis. Like you're manufacturing the small parts, right? But assuming they design a big roof of a stadium, but can you analyze the roof using the Inspire and the wind load, the structural, etc.?
So if a small part is 200 wide, a big part is 200. Yeah. What I want to say, the software underneath, which is running on the CPU, that does not see whether it is a millimeter or a meter or a kilometer. That just sees the 200. So the big or small in the mathematics, there is no big and small. So we can run full stadium exactly with the same method as a small ant. There's no difference. Yeah.
Can you analyze the wind load like in Hong Kong with typhoon, etc.? Can you analyze those stuff as well?
Yeah.
Wind load is well.
Yeah. So we have actually a CFD tool where you simulate the wind, the airflow through a city, and you derive the loads on a single building, and these loads later on you bring into Inspire, and you can run the deflection and stresses. But you cannot calculate the wind loads in Inspire. You can only calculate the response of the building based on the wind loads. So the wind loads have to come from somewhere else or from a CFD simulation that can be run in our tools using the same licenses.
I want to ask you
how
many materials you use?
How many materials? Oh, there's a big question. What is a material? I mean, metal. You can have metals, different types of aluminiums, different types of plastics. I think the variety is really wide. Yeah?
Let's put it this way. What sort of material cannot be used in 3D printing?
I've not seen glass yet, but so far, more or less. Concrete, you do. Concrete, 3D printing for buildings, metals, plastics, glass. I'm pretty sure they will do it soon.
In one model, you use one single material, or you combine materials. Multiple.
In general, we have one material, but it can use as well multi-material.
What is the material for?
The nozzle? Oh, I think it was titanium.
So the melting point of the titanium should be higher than the melting point of the material to be printed.
The melting point of
the nozzle needs to be higher.
Yeah. No, right. Yeah.
The property of materials, you have this like generic or standard setting. Can that be like changed to see? Yeah, can be changed.
So you can bring in your own material library, because the material library is often the most expensive or most valuable treasure of a company. And when you go to Daimler and you work with BMW, you will never get the material library from them in a way that you can copy it. So that is where these companies put a lot of effort into to get the exact values out of testing, out of simulation of the micromaterials, and they build material libraries, and we can import them into our software and use whatever material you have.
Does China
Which kind of material? Metal.
Yes. China. So just only the Europe or the USA.
No, that's not a problem. So first of all, these machines are circling around all over the world, so you can buy them wherever you are. Just have to buy it and have the money. Spend the money, and there are some manufacturers of 3D printing machines as well in China. We work with some of them, BLT for example, and I'm sure they print metal, and then it depends how, it's no problem. In Taiwan they have as well a lot of knowledge about it, how to do that printing machines.
Can I ask one last question here? Because your software seems to be assuming that the whole thing is monolithic. In other words, it's made of one material. I mean, let's say if two materials are put together, let's say concrete and steel, can your software handle that situation?
Do you still allow everyone to ask one last question?
Seven! That allows one last answer.
So Tony might be able to answer what is possible in Inspire. I can just say that the software in the background has no problem with multi-material optimization. Even the how do you call the shift between both materials, where to put which material, is possible. But you can say if that's possible in Inspire.
Or you can have multi-parts as multi-materials, but I would say if you're building a bridge and you want the optimum kind of member layout, it's pretty much going to be the same layout whether it's concrete, reinforced concrete or steel. It's just how much concrete and reinforcing will you put in versus how many steel columns. So Inspire still tells you where to put the material, no matter what the material. It's just, it might be more, but it will still become aligned the same. Or you might need extra supporting for buckling. Your main locations don't seem to change very much. A final answer? Yeah. So final questions?
Then you wrap up this section.
Is everyone hungry?
I can still do more.
That's good.